Welcome back. Now, in part 4 of our video series, I'm still gonna be focused on linear functions. That much hasn't changed, but I'm just gonna move to a different aspect of linear functions and address a slightly different aspect of linear functions that I didn't get to touch on the part 3 of the introductions, and that part has to do with the m, or our gradient, or our slope. Now, just to jog your memory, I did say that when our slope is positive, we have a graph that is increasing from left to right, such as the one is in this scenario here. This is what we get when our gradient is positive. And when our gradient is negative, we get a graph that looks a lot like this one in here. I did also say that when our gradient, our line is vertical, meaning our line is parallel to the y-axis, the gradient is undefined. When our line is parallel to the y-axis, the gradient is undefined, meaning the gradient of the y-axis itself is undefined. I did also mention that when the gradient is parallel to the x-axis, the gradient is equivalent to 0, meaning the gradient of the x-axis itself is equivalent to what? To 0. Now, I'm gonna move on to now address a slightly different aspect, or break down further the concept of the gradient as how it affects the relationship of one straight line to another. Now, in this particular scenario in here, I'm looking at a series of functions. I've got one function which is represented by line AB. The next function is represented by line CD. The other function is represented by line EF. Now, by all means, I do need you to make note of the fact that in this case, illustration in here, line AB or graph AB is parallel to graph CD. Now, seeing as graph AB and graph CD are parallel, we can then deduce that if AB is parallel to CD, therefore the gradient of AB is equals to the gradient of CD. Why am I telling you this? This is to say to you, whenever, always and forever, when two lines are parallel, such as in the case of AB and CD, the two lines or the two graphs have equal gradient. I'm going to say it again. When two graphs are parallel to each other, meaning when two lines have an angle that is neither increasing or decreasing between them, they're as parallel as railway lines, they have equal gradients. I'm repeating this on purpose because you need to remember that. Moving on. Now, what happens of lines that are now perpendicular to each other, meaning the two lines that are now meeting at 90 degrees in relation to one another? Now, such an example we get here. Let us observe line EF and line AB. In the case of line EF, let us suppose that we are given that line EF is perpendicular to line AB. When two lines are perpendicular to each other, or when two lines meet at 90 degrees with one another, we can then say that those two lines, when AB is perpendicular to EF, therefore their gradients, when we multiply their gradients, when we multiply the gradient of AB with the gradient of EF, you should be able to get what? -1. Why am I telling you this story? I'm telling you this story because always and forevermore, when you have two perpendicular lines, when you have two lines that are meeting at 90 degrees to one another, the product of their gradients is always going to give you -1. So when two lines are perpendicular, when you multiply their gradients, when the product of their gradients is going to give you -1. Any inputs or questions? Going once, going twice, solved. Now, if you've got any inputs or questions, please don't hesitate to hit the the comment section. Don't hesitate to hit the Q&A section in our inner circle group. Now, moving on to the next aspect. Every function has a domain and a range. Like if you remember earlier on in this video series, I did mention the basic terminologies that one needs to be familiar with. It specifically relates to function, and one of those definitions is the domain. Now, the literal definition of a domain is a set of x values. So a domain of a straight line function is always defined as x element of real numbers. Now, what of the range? The range is literally the literal definition of range is the set of x, y values, meaning the range has to do with only y values. As such, the range of a linear function is always defined as y element of real numbers. Domain, x element of real numbers. Range, y element of real numbers. Easy enough, ne? I believe so as well. I believe so. Like, give yourselves a round of applause for hanging on up until the very last second. Now, without further ado, I am gonna be wrapping this up and prepping to go into the next part. Now, into the next part, that's where I need you to pay rather meticulous attention, seeing as we will be getting into the part of sketching functions. After sketching functions, now we are going to be getting into the aspect of now us using a given sketch to determine the equation. Thank you very much. See you in the next one.